So I'm Katherine Woodruff at New Mexico State, and I'm going to talk about work we're doing in MicroBooNE using gradient-boosted decision trees for proton track ID. So a little physics motivation. We're interested in the spin structure of the proton, and so the net spin of the proton is a combination of the spin of the quarks and gluons and the angular momentum. For our specific analysis, we're interested in the net spin of the strange quark. So this delta S is just the strange quark and anti-quark flavor spin in the direction of the proton, and then minus the spin of them in the opposite direction of the proton. So this was expected to be 0 because you have all these strange anti-strange pairs being created and annihilated, and you would think it would all average out. But back in the 80s in charged lepton deep inelastic scattering, it was found to be negative. There were some assumptions like sp3 flavor symmetry, and there was also quite a bit of uncertainty on the measurement. So what we want to do is measure it in an independent way that doesn't make these same assumptions. So you can do that in neutral current elastic neutrino proton scattering. So here's the cross-section for the NC elastic scattering, and you can see these G's here are form factors. So they represent the finite structure of the proton. So you have the electric, magnetic, and then this axial form factor represents the spin structure of the proton. So at low q squared, or at q squared equals 0, the axial form factor is just a combination of the net up, down, and strange contributions to the spin of the proton, and this U and D part has been measured in neutron decay. So you can determine delta S if you measure this NC elastic cross-section at low enough q squared. So this has been done before at the E734 neutrino experiment at Brookhaven Lab back in the 80s also. They were able to get down to about half a GeV q squared. And they also found delta S consistent with being negative, but again, there's a lot of uncertainty, and this is mostly because, you have to extrapolate to q squared equals 0, so the shape of your form factor, the choice you make for that is really important. So the reason this is a hard measurement is because basically you have a neutrino coming in, scattering off a proton, and the neutrino exiting. So all you have is just one short proton track. And then low q squared means low kinetic energy of the proton, so the closer you get to 0, the shorter the proton. So what you need is a really dense, high-resolution neutrino detector, and that's what liquid argon TPCs get you. So Kevin already did a nice explanation of this, but a refresher if any of you weren't here. This is how liquid argon TPCs work. So here's your TPC. This is filled with liquid argon. A neutrino comes in, interacts with the argon. The charged particles coming out ionize the argon, and the electrons from the ionization get drifted through an electric field to the anode here, where we have a bunch of wires strung up. The electrons hit the wires, and we can read out the signal. So here's an example of, these are all the wires going like this, and this is a nice neutrino interaction in MicroBooNE. So MicroBooNE, we have 3 of these planes. So this is one neutrino event, the same one Kevin showed earlier. And so you can use the 3 planes plus the timing information to get a nice 3D reconstruction of these events. Each of the planes is 3,000 wires, and we read thousands of time ticks per event. They're 10 meters long, so these are huge events. Each event is about 30 megabytes. So it's a lot of information per event. So here we installed about 2 years ago. We've been running. We have about 200,000 neutrino events on tape right now. Okay, so back to the neutral current elastic signal in MicroBooNE. So this is an example from simulation of what one of these events would look like. This is a neutral current elastic proton that's been scattered. We think in MicroBooNE we can measure these if they go about at least 1.5 centimeters, which is about 5 wires. And that would correspond to a q squared of 0.08 GeV, so much lower than has been measured before for delta S measurement. So we expect about 10,000 of these events during the total runtime, or 3-year runtime. But the problem is that only makes up about 5% of the neutrino interactions, which only make up about 1% of the triggered interactions, because we have a lot of cosmics. You can see we're on the surface. So yeah, this nice, pretty proton event is just this tiny little 2-centimeter square in our 10-meter detector. And I don't know how well you can see, but there are lots of cosmic tracks all around. So we can't hand scan these. You can't find 10,000 of these and 2 million of these. So we need to do automated event reconstruction, which is really newly developed. A lot of people in MicroBooNE and GBDT are working on it. So yeah, so the first thing you think is, you know, CNN. This is this beautiful square little picture you can scan over convolutional neural nets. But again, this is, you know, about 20 million pixels times 3 in about 2 million events. So that's, we want to be able to reduce that a bit. And if you look, so for these, just, we're not looking at showers or, you know, deep elastic scattering. We're looking at straight short tracks in a bunch of zeros. So we can reduce this problem a lot just by trying to get the tracks out first. So what we do first is we just find the hits using fitting Gaussians to the waveform. So this is one waveform, so just one line down this. And we get a nice efficient set of hits on all the 3 planes. Then we can just cluster those hits into lines and match them across the 3 planes and project them into 3D. And we have a pretty efficient then track finding algorithm that finds, see here's this, this is a cosmic event in MicroBooNE, but you have about 20 track objects, which is a lot better of a classification problem than, you know, tens of millions of pixels. So this makes the classification a lot easier. So the goals for classification are, we have 2 main ones. So first, to figure out which tracks are neutrino-induced and which are cosmic-induced. And then the second one is, once we have those neutrino-induced tracks, you know, what particle type are they? What actually happened? Are they protons or muons? What? So some of the features we use to help with telling cosmics from neutrino-induced, or, you know, the position, is it coming in the top of the detector, is it downward pointed, or is it forward going with the beam? And then also for, like, what type of particle, there's obviously, like, the how long is it, how dense is it, how much charge was deposited, and the shape of the charge deposit. So we can't use any 1 or 2 of these features to identify each track, but we can use a machine learning algorithm to optimize using all of the features at once, and we can also combine our 2 classification goals and classify both at the same time. So whether it's a neutrino-induced and what type of track it is. So we decided to do that using decision trees, mostly just because they are conceptually similar to traditional physics cuts, so they're easily interpretable, and the rest of the collaboration is happy with it. Ish. And then, yeah, so what we're using are regression trees, which are decision trees, but instead of yeses or nos, you have continuous variables. And then the boosting is just, it's an ensemble method by combining a bunch of, you know, weak learners, individual trees, to make a more powerful predictor. And then in boosting, for those who don't know, each tree is created iteratively, so you train each new tree based on the misclassification of all of the previous trees. So, okay, and then we use XGBoost. Mostly we chose it just because it's really popular, it's really well supported, and it's easy to use. So this, I'm going to go over is the algorithm, and so the gradient boosting algorithm specific in XGBoost for people that are more familiar with other boosting algorithms. So basically, the prediction for each track is the sum over the predictions of all of the trees. So this f of k represents the tree structure for the kth tree. And then the goal for creating these trees and training is to minimize the subjective function. So you have the loss here, which is basically the difference between the prediction and the truth. And then you have this regularization term, which just penalizes the complexity, so you don't overfit, essentially. Okay, so then the gradient boosting, the way it's done in XGBoost, is this cool trick. So when you're making your teeth tree, your loss function is the difference between the truth and then the prediction of your existing set of trees plus your prediction of your new tree. Because remember, it's just the sum over each tree. So then you can simplify this by doing a second order approximation. So this, your loss function turns into your loss function of your existing set of trees plus the derivative of that loss function times the prediction of your new tree, and then the second derivative and the square of the prediction. So basically, you only have to compute your loss function once per new tree you're trying to train instead of having to compute the loss function for every single possible split you could make, which is very, it reduces the computation a lot, makes it a lot faster and a lot more powerful. So then what we're doing in MicroBooNE, so we're trying to classify 5 different types of tracks at once. So we have one classifier, and it tells us whether this is proton, which is either both neutrino-induced and cosmic-induced protons are here, and then muons, pions, or electromagnetic stuff from neutrinos, or then any other type of non-proton cosmic are the 5 classes we use. So basically, here's an example from, this is a data event in MicroBooNE. We put in this reconstructed track. Well, this is the raw data, but the reconstructed track has about 20 of those track features that I described earlier, like position and charge deposited and stuff. And then it outputs what type of particle of these 5 types of classes it thinks it is. So this one thinks is very likely to be a proton. So that looks good. And then our performance in MicroBooNE. So here's the efficiency versus purity for our simulated events. The different points are for different scores that you decide to cut on for protons. So you can see that there's a trade-off, but we get, there's a nice area in the middle where you can have both a fairly high purity and efficiency. And then this here, so this is all of the neutrino-induced protons that we simulated in light blue, and then the ones that were reconstructed by that hit-finding track-finding algorithm are in the dark blue here. And then, so of those reconstructed tracks that we input into the decision tree, the red is the ones that were correctly identified as protons. So you can see the identification efficiency is high across all levels of kinetic energy. So even down here at low Q squared, which is where we really want to fill in that data. And then here's the background. So this is everything that got classified as a proton, all of the reconstructed tracks. So here are the protons in blue. You have the neutrino-induced protons in dark blue and the cosmic in light blue. And then the backgrounds, we have the non-proton cosmics and the neutrino-induced non-protons. So again, you can see that we have a pretty high purity. And the reason there are just so many more cosmics than neutrino-induced is just because we start out with, about 100 to 1 cosmics to the neutrino-induced tracks. So, okay. And then just to show that this can work in data too. So we haven't done full data studies yet, but we ran over a subset of our open data, and we looked for a track that was likely a proton and didn't have any other tracks around it, so it was nice and isolated. And we found this really nice-looking neutral current candidate. And then we can also do the same thing with the same efficiency for just requiring or asking for a proton track that's connected to something that was called a muon, and we get this nice-looking CCQE candidate there. Okay, so just to summarize, so you can determine the net spin of the strange quarks in the proton in neutrino NC elastic scattering, and MicroBooNE will be able to make a measurement at Q squared lower than other neutrino experiments have made before. And so we can reduce the dimensionality of the classification problem by reconstructing tracked objects first. So we can go from about 30 megabyte events to just 20 floats. And then we can accurately classify protons using gradient boosted decision trees.
Future plans for
yeah, so right now we're in a stage where we're making improvements to the track finding algorithm that comes before this. So this is already working really well, like once we have reconstructed tracks. So all of our efforts right now are going into being able to take the raw hits and make improve the efficiency of just finding the tracks to input to the particle IDs. So that's already, we've already made big improvements, which we don't have plots for yet, but yeah, improve our efficiency.
any sort of comparison with the network-based?
No, I don't have any direct comparisons. So most of the like deep learning and network stuff in MicroBooNE is for specific like other analysis. So we have the low energy excess, which has electron neutrinos, and then like neutron decay. So no one's tried to do neutral current with networks.
Okay, also let's thank our speaker.